Oh, shoot. Do you know what tennis balls and digital PCR has in common? It's Poisson statistics and random distribution. Let me show you. This tennis court offers a perfect way to explain Poisson statistics in a simple way. We are going to show you in a simple way how we can use partitioning instead of a bulk reaction. So this was hard for me to find the target molecule, the tennis ball, in a bulk reaction. Poisson statistics is all about random distribution, and that is what we use, the power of that statistics, when we actually start to randomly distribute the target into the partitions. By that happened, we actually are increasing the effective concentration. So the competition within each partition now perhaps has our target tennis ball together with one, instead of in bulk reaction where it's completely covered, so it's impossible to find it. So we have thrown 20 tennis balls into 20 buckets. Is every bucket filled with a tennis ball? No, they are not. Because of random distribution, the blue tennis ball and the yellow tennis ball will end up randomly into these partitions, or tennis balls if you will. And our nanoplates work the same way. So the blue tennis balls are ending up in a bucket, perhaps together with 1 or 2 yellow tennis balls. But most importantly, 1/3 of the buckets will be empty. So the partitioning, throwing randomly into partitions, has proven much better way to find the blue tennis balls than in this situation. So the situation we don't want is a situation where we have the yellow tennis ball in all the buckets. Because we are using the empty ones to be able to calculate the concentration. So how our algorithm works is that we are validating all the partitions with the reference diet within our master mix. So that is the valid partitions, meaning accepted partitions, accepted buckets that we use for calculations. If we have a target in each of these, we call that the valid partition. So if we have the valid partitions, then we actually withdraw the positive amplified partitions. So if we have the same amount of positives as valid, we cannot calculate the concentration. So that means the volume needs to be exact. So that is why we are implementing the volume precision factor. So how does that work? Well, here you have 2 nanowells, well A and B. So as you know, this bucket, if I fill this with water and I fill this one with water, and then we measure the volume, it will not be the same because they are made differently and not perfect. The same conditions are in our nanowells, and this is what we are aware of. And using Poisson statistics to be able to calculate, we need the volume to be constant. All the buckets within A has the same volume, but it's a slight difference from B due to the manufacturing part where we use a stamper. So that is what we are actually putting into the VPF. So we are compensating for the differences, the small but very there differences in volume, to be able to calculate the concentration exact. So what sets the limit of detection? Well, it's simple. It is the rule of 3. So if you want to detect 1 tennis ball, you actually need to screen 3. So the lower limit of detection set by digital PCR is actually based on the amount of DNA or amount of tennis balls you have. The dynamic range, however, is set by the number of buckets you have available. So that is why the 8500 nanoplate has less dynamic range than the 26K plate. So now you have learned how a tennis court can teach you about Poisson statistic and random distribution. Up next, in deep PCR, absolute, not relative, behind the scenes and the assembly of QAIGEN. Stay tuned.
QAIGEN.
Sample to insight.